Okay, so in this lecture we're going to start building up the machinery necessary to prove that rings of integers are finitely generated free O module or Z modules. Sorry. And the first piece of machinery is we need the notions of norm and trace. In particular, trace is going to be the kind of the more important of the two, but norm will definitely play a role later in the course. So in this lecture, so what are we going to do? In this lecture, we're just going to define what the norm and trace are, and then we'll just do a couple examples. In the next lecture, we'll prove probably like one of the most important facts about norm and trace, which relates Galois theory to these norm and traces in the number field setting. Okay, so first I want to just kind of give you some motivation for what these norm and trace maps are. So in the study of number fields, it can be helpful to think of let's say, of an extension L over K as L being a K vector space, being, I guess, not just a K vector space, a K algebra. Okay, so this is L is a ring with a K vector space structure. So this is definitely a K algebra, and we can view elements of L as K algebra homomorphisms from L to L. So how do we do this? Or I guess not K algebra homomorphism, sorry, these should be just K linear homomorphism. As K, right, linear homomorphisms. Given an L, given an element little l in L, this corresponds to the K algebra homomorphism maybe X maps to, sorry, again I said K algebra, it should be K vector space homomorphism. X maps to L times X. So it's essentially L corresponds to the K linear homomorphism multiplication by L. And when we think of these things in this way, we can associate to elements of big L matrices with entries in K. Okay, so if we choose a K basis for L, then we can think of L as a matrix. Okay. Basically the one associated to the multiplication by L map. So from here I can get a matrix A with entries in K. Okay, we can think of L as a matrix, the one associated to multiplication by L. So this is the idea which gives rise to trace and norm. Okay. So this idea gives rise to trace and norm. So how do I actually define the trace and norm? Okay, so let me go ahead and give you the definition. So it's going to be more general than two fields, because oftentimes we'll want it in the ring of integers case. So I'm going to let A contained in B be an extension of rings. And there's an assumption we want to make about this extension such that B is a free A module of rank n. So we can't define these necessarily for any extension of rings, but if B is a free A module, then we're in business. A finitely generative free A module. I'm going to pick a basis, B1 through Bn, be a basis for B over A, and so for B and B, we write B times Bi equals sum j equals 1 to n Aij Bj Aij A. So what are we doing here? We're essentially writing down the matrix of multiplication by B. So when you're thinking of this, you should be thinking that this matrix Aij is the matrix of multiplication by B. Okay. So basically, so why is this the right matrix to look at? B times Bi, that's like the element B acting on this, the ith basis vector. This is essentially like, if you're thinking of this as the ith, like standard basis vector, so with a 1 in the ith coordinate and zeros elsewhere, then this should pick out the ith column, and this is telling us the ith column is Aij, where j runs from 1 to n. So this is the matrix that we're talking about up here. And then from here, then we define the norm and trace of A, or of B, sorry, of B by, so the norm, and so you have to be a little careful here. If there are lots of rings floating around, so if A is like sitting inside, if A is sitting inside B and B is sitting inside C, you can talk about the norm from C to B or the norm from C to A, and they're not quite the same. So you have to be a little careful. I mean, there's a relationship between them, but they're not the same. So if there's many rings floating around, you need to be careful and specify this. But the norm of this element B is the determinant of this matrix Aij, and the trace of an element B is just the trace of the matrix Aij. Okay, so you can say, like, well, I guess there's a slight concern. What if I pick a different basis? The same way that you prove that determinant and trace are basis invariant, in the linear algebra case, those proofs will show that norm and trace are invariant in this case. So, let's say here, there are a couple properties that I'm not going to prove. They're all the properties you know from linear algebra. So we're going to let A and B be as above. So this should be, I should be labeling these things, to be honest. This should be 16.1, and this should be 16.2, or 17. Almost forgot where we were. Seventeen point one. 17.2. So we're going to let A and B be rings as above. And we're going to say let B and B prime, B and B, A and A. Then, what can we say? Trace of B plus B prime. Well, the trace is additive. Okay. The trace is A linear. And the trace is, what should I say? So, if B is free of rank n, then elements of A just go to A to the n. So how do you see this? It's because A times Bi is just A Bi. So the matrix associated to an element A is just the diagonal matrix A. Okay. And then there are other properties of the norms. The norm is multiplicative. And the same thing. Oh, sorry, I made a mistake here. This should be n times A, and this one should be A to the n. Sorry. The logic I said works, so if the matrix looks like A, then the determinant is A to the n, and the trace is the sum of the diagonal entries, which is n times A. Okay. We're not going to prove this. And I'll make the remark. So this is 17.3. If, I guess, the notation B over A is omitted if it's clear from context. So in this example above, I didn't write B over A everywhere because those are the only two rings, and so this is kind of like the only, I guess you could talk about the trace from A to A, but it's kind of redundant and no one would really do that. And if they did, they would specify and let you know. Okay, so this is with the traces, and I just want to end with a couple examples of norm and trace. So the two examples, yeah, I guess maybe first let's do a specific example. So this is 17.4. Consider, let's say A equals Q, B equals Q adjoin I, and yeah, let's try C equals Q rejoin a fourth or an eighth root of unity 2 pi I over 8. Okay, so we see, that we have containment to A, B, and C. And what I want to do is, let's compute maybe the norm from, let's say, B to A of something simple. Let's just do the norm from B to A of I, and let's compute the norm from C to A of I, and the norm from B to C of I. Okay, so here are three, from C to B. Gosh. It should be from C to B. What? Okay. So, first, the norm from B to A of I. Well, okay, so the first thing that we're supposed to do is figure out a basis for B over A. Well, B has basis 1I. Okay. This extension here is of degree 2. This extension here is of degree 2. Just making sure I'm not making any mistakes here. Yeah, I think this extension here should still be of degree 2, because I think the whole thing is of degree 4. Okay, so B has basis. This guy has, I guess, Q basis. Should be specific because we've got a lot of rings floating around. In this basis, okay, we have, so I times 1, that's just 0, 1s, and 1I. And I times I is negative 1, 1s, and 0 i's. Okay, so our matrix, I just take these coefficients. Our matrix of I in this basis is 0, 1, negative 1, 0. Okay, and this matrix has determinant 1. Okay. Maybe I somehow picked a bad example, I'm not sure. So the norm here, in this case, is 1. Okay, so let's do the next one. Norm from C to A. Bye. So first we need a Q basis of C. Now, this basically will be all the eighth roots of unity. So this will be, I guess, sorry, not all the eighth roots of unity, all the primitive. I want to say that we can take, sorry, okay, it's not all the primitive either. I want to say that we can take, so this guy, 2 pi over 8. Maybe I and e to the 3 pi over 8. Okay, yeah, we can take, I think this will work. I know this space has dimension 4 over Q, so it suffices to show that these are these span as Q vectors, that these span. So to prove this is a Q basis, so I guess there are two claims here. We need one that dim C over A equals 4, and 2 that this set spans. Okay, so let's maybe actually go through and prove these, because I think this will be, at the very least, it'll be a good exercise for me. Okay, so how do I prove this thing has dimension 4? Oh, I just need to know what the minimum polynomial for this guy is over Q. Okay, so dimension of C over A equals the degree of the minimal polynomial for e to the 2 pi I over 8 of x. Okay. Now this is okay, so I think this, I claim, this is x to the 4th plus 1. Okay. So I can check very easily that this is actually a root of this guy. So you know, if this yeah, okay, yeah, so note e to the 2 pi I over 8 is a root of x to the 4th plus 1. Okay, I just need to check this polynomial is irreducible. However, we can actually do some, like, we don't actually have to do any like real math to check this is irreducible. This is irreducible because oh, I guess here's one way to say it. So because dim C over A, I now know it divides 4, or okay, maybe, okay, here's how we'll do it. Because 1 dim B over A, so by the Tower law, this guy divides dim C over A, so that 2 divides dim C over A. Okay, so this automatically implies that this together with this implies that dim C over A is either 2 or 4, because it's a number less than 4 divisible by 2, or less than or equal to 4, bounded above by 4. And 2, it's not equal to C is not equal to B, since, well, one way to tell is that Q adjoint I has no 8th roots of unity. Okay, so if this is not equal to b, then this implies that the dimension of C over A has to be bigger than 2, which implies that it's 4. Okay. Okay. So I've got this first thing checked off the list. The second condition, I just need to check the spans. So let's just think about this graphically. Certainly, so certainly the collection 1 e to the 2 pi I over 8 I e to the 3 pi I over 8 negative 1 e to the 5 pi over 8 and so on. All the eighth roots of unity span. Because everything here is essentially an irrational polynomial in this guy, and the powers of this thing are one of these eighth roots of unity. Okay. However, if I'm thinking about the unit circle, maybe I'll draw this picture a little bigger. Okay. So I'm thinking about the unit circle. I've got all my eighth roots of unity. So I need to show that I now need to show, so it suffices to show each eighth root of unity is in the span. The Q span of these guys. 1 e to the 2 pi I over 8 I e to the 3 pi I over 8. Okay. However, so the guys I've got picked out for this basis, these look like this point, this point, this point, and that point. And notice that the opposite points here, the other eighth root of unity, are all opposite to one of my red points. And to get the opposite point, I just have to take the negative. Okay. So note negative 1 equals negative of 1 e to the 5 pi I over 8 equals negative e to the, what the hell am I doing? I've been screwing this up. This should be 6. This should be 10. Sorry. Cut this all. It should be 10 here. Okay. Yeah, I should be 6. Okay. E to the 10 pi I over 8 is negative e to the 2 pi I over 8. And so on and so forth. Okay. So just by taking negatives, I get all the eighth roots of unity in the span of these guys. So this is actually the basis. Okay, so what's the point? So thus 1 e to the 2 pi I over 8 I e to the 3 pi I over 8. Gosh. It should be 6 pi. Is a Q basis for C. Okay, in this basis, let's write down the matrix for I. Okay. Should just be the letter C, not bold. In this basis, Ix by, okay, so I times -1, or I times 1 is just 0, 0, 1, 0. I times e to the 2 pi I over 8. Okay, so this, in our picture, rotates this guy by 90 degrees. So this is going to be 0, 0, 0, 1. I times I, that's -1. So this is going to be -1, 0, 0, 0. And I times e to the 6 pi I over 8 rotates again by a quarter turn. That's going to be negative this one, so it'll be 0, -1, 0, 0. Okay, these are I think I may have this matrix transposed, but it actually doesn't matter for the tracer determinant. Okay, so we can compute the determinant. So Ix by, okay, let me just think, I want to get this right. According to this formula up here, it should be 1, 2. Okay, so actually no, this isn't transposed. Okay, yeah, I think this is right. Okay. -1, 0, 0, 0, 0, -1, 0, 0. And the determinant of this guy, okay, we need to expand along columns or rows, whichever you like. So this will be determinants, so put in absolute values, and okay, we're taking the determinant. Determinant of this guy is going to be, so I need to apply the sign here. So it'll just be the determinant of this guy. Uh, 0, 1, 0, 0, 0, 1, -1, 0, 0. Okay, expanding along here. So this is positive, negative, wait. I think there should be a negative sign here. Positive, negative. Okay, so this is going to be a positive, so I'm going to get another negative out. Okay, 1, 0, 0, 1. Okay, which is just 1. Okay, so we found that the norm from A to C of I was 1. Yeah, okay. Now, the last computation, so the norm from C to B of I, we can actually use this fact. So the norm from C to B. I, well, I is in B, so this is just I squared, which is -1. Okay, and so this is by, what, 17.3? Or no, 17.2. By 17.2 here. Okay, and we see, so note, norm from A to B times the norm from B to C to B was the norm from C to A. -1 times -1 is 1. We're not going to prove that, but it is a general fact. And it shows you that, you know, it does actually matter which rings you put down here. Okay, so this finishes up this example, and this finishes up the introductory lecture to norms and traces. Next, we'll talk about how we can use Galois theory to actually compute these things in the number field setting.